Okay, continuing section 3.5, we're going to create a linear model from a table of values where the y-intercept isn't actually given to us, but we're going to use that additive property of the slope in order for us to get there. So the first thing that I'm going to do is I'm going to find the constant rates of change from here to here and here to here. If there wasn't constant rate of change, you know that it wouldn't be linear. So I'm just going to verify that in each and every case. So from 4 to 8, we're increasing by 4. And from 8 to 12, we're increasing by 4. Remember, to get that, we could just as well do 8 minus 4 and 12 minus 8. And then over here, let's do the same thing from the y's. Negative 4 up to negative 7, that's actually decreasing by 3. Again, if you need to do that with numbers and math, it's negative 4 minus the bigger one, sorry, the second one is a negative 7 minus a negative 4. And that way, we're doing the same thing. And you'll notice that that's just the difference quotient, right? Doing individuals here and here. And from here, it's negative 10 minus a negative 7, which again gives us our negative 3. And so we see we do have constant rate of change, and then we can write our rate of change, I'll call it R of C, as our dependent changes, which are negative 3's, over our independent changes, which are 4's. And because these are constant, we could take any two of these ordered pairs and do the difference quotient that we're so used to doing, which you see on this side over here, which would form the numerator, and this side over here, which would form the denominator of one such difference quotient. Now, once we have the rate of change, the next thing that we need to build our model is the y-intercept, but you know, we don't have it. Well, not to worry, we can actually find the y-intercept because we can move backward the same way that we've been moving forward. So to go from here to here, we had to subtract 4. So this would be subtract 4 to move back here. And from moving from here to here, we've been subtracting 3, but now we would add 3. And so what we're going to find is the next lowest one is 0, and the next lowest one here is a negative 1. And that is our y-intercept. So our y-intercept is a negative 1. And now we can build that model. Y is equal to negative 3/4 x minus 1. And there we go. There's the model. Now the cool thing is, with this model, we can check and make sure that it works. So I'm going to change the page and we're going to do a check on this. So remember that any of our ordered pairs should satisfy this equation if it's truly the linear equation for this table. So the first thing I'm going to do is I'm going to plug in one of my values. And I'm going to plug in the first one, 4, negative 4. So if I put in 4 here and negative 4 over there, right, substituting those in, I'm asking, does this satisfy it? So this says negative 4 is equal to, and of course it is questioning, right? And then we cancel, and that says negative 3 minus 1. And that says negative 4 equals negative 4. And so it does indeed satisfy it. It forms a check of that. Now I can do it again for another one of them. So let's take the 8, negative 7 and check it. So my y is a negative 7, and that's equal to, and I'm questioning, and that's negative 3/4, and it's times a positive 8, and then minus my 1. So these cancel, and that's going to give me negative 6 and negative 1, which gives me a negative 7. And negative 7 equals negative 7, and so it does. And if I had time, I'd do the last one to show you as well. So here's a summary right here if you want.